and then.
Okay.
Yep, you're good to go.
Now, is that good? You never know until you try it.
Perfect,
okay,
thanks.
so thanks very much for inviting me to speak this evening. I was given 15 minutes, so I'll stick to that, and it's late in the evening. So, and just to talk a little bit about soils and water quality, just to say from the offset, the videos there, and also what I've seen of the Smart Farms initiative, I think it's a very good idea in the ASAP program. And I'm going to just highlight just 2 or 3 things that from research and some of the research behind it that I think are important for water quality protection, just very briefly. So first of all, images like this illustrates why soils and water quality are connected. So how we manage the soils, and in a case like this, when you have a heavy rain event and saturated soils and you get runoff, and you get a lot of sediment running into the streams, which is probably carrying a lot of phosphorus with us as well. So what we do on the land affects water quality. Very quickly, just to give an overview of water quality in Ireland, from the latest report, you can see, in fact, by European standards, we have relatively good water quality in general, but as you can see there, we have significant amounts of our rivers, in this case, in only moderate or in poor water quality condition. And there are a few things about trends in recent years that unfortunately are going in the wrong direction in terms of water quality. So again, from the most recent report for the water quality status, 18% showed declines, 14% showed improvements, but of course that's more in the decline than in the improvements, which isn't the direction that we want to be going. In particular, one thing of concern with water quality is the highest quality water bodies that we have. These would be in the dark blue there. That's what we would call Q5, which is the highest quality. That's like pristine water bodies. And you'll see there from the late 80s, they've dropped from about 13% to less than 1%. So that's a trend that we don't want. Of course, there are many threats to water quality, and nutrients, for example, come from wastewater treatment, from urban sources, from industrial sources, etc. But from the EPA assessment of the threats to water quality, as this figure illustrates here, agriculture is the most often the threat to water quality, and that is in a way no surprise if you look at the other bar chart or the other pie diagram there. Agriculture, of course, makes up most of our land use. So, so we do have work to do on agriculture and water quality. Another trend, just to show in a map form here, this is nitrogen concentrations in rivers on the left and phosphorus concentrations on the right. And anywhere where you can see a red dot there, the concentrations in the rivers have been increasing, and you can see that pattern to the east and the south. And that's the, obviously we want to try to halt or reverse trends. Likewise, this is an estimate of the total amount of nitrogen and phosphorus being discharged by our rivers. And you can see how up until about 2012 or 2013, they were on a downward trend in both cases. But after that, unfortunately, they've both started to rise. So we don't want them going that way. As I said, agriculture is only one source of this nitrogen and phosphorus, not the entire picture, but it is a part of the story. So agriculture, as I think others have been already saying this evening, needs to be part of the solution on it too. So what can farmers do? I'm just very briefly going to highlight 2 or 3 things and some of the research that's behind it. So first of all, as has been mentioned, right, soil testing and nutrient management planning, good nutrient management planning. What you don't know, you can't manage. So we have our index system, which probably we're all familiar with, index 1 to 4. where 4 is above optimum, and it could be more risky in terms of phosphorus loss to water. So trying to keep our soils in optimum index 3 and out of the index 4 through good practice of soil testing and then appropriate nutrient management with that. As was mentioned there, I used to work with John on the agricultural catchments programme. We would have looked, for example, in the Timoleague Catchment, which is down in Cork, quite well drained soils and dominated by dairy farming. And we would have looked at the soil phosphorus status on the farms in that catchment over time. So that's 2010 and then 2013. And you can see how over time, in fact, the farmers in that catchment did manage to improve their soil P fertility with the index 4, areas of index 4 soils dropping and areas of index 3, the optimum, increasing. And so we looked then in these catchments, because the water flowing out of these catchments is being monitored to see, could we see, was that improvement in soil fertility management, did that then match up to an improvement in water quality? And in fact, we found that it did. And what we're showing here is, just to draw your attention to the kind of take-home message from it, if you just look at the top lines there, what's called quick flow, that'll be runoff that's coming quickly off of the fields, for example, in big rain events. And up the side there is phosphorus concentrations in the water. And you can see over time that those phosphorus concentrations were coming down at the same time that our soil P concentrations, the index 4 soils, were coming down. So that was a sign that through better soil fertility management, which is good for the farm and the performance of the farm, we also could improve the water quality potentially. What we found, and in other studies as well, repeatedly find when you look at individual farms and when you look down to the individual field and paddock sort of level in soil testing, is that you get the full range of indexes in many cases across the farm, from index 4 to index 1 for phosphorus. And often this reflects past practices like slurry application, for example, to some fields year after year, so that they build up phosphorus, for example. But what that represents is that phosphorus is being distributed in a very unbalanced way across the farm and in a non-optimal way. So both for the environment and for the performance of the farm, grass growth and quality, that's not the ideal. So one of the key things that emerged from that is, again, the importance of soil testing, and ideally, in a sense, the smaller the area you can soil test, the better. So down to field and paddock scale, all the better, that you then know what the soil phosphorus status is and then can manage the phosphorus appropriately. The second thing I'd just like to say is that, so that was the soil testing important. The second thing I think is that soil type is important. So if I just show here two very different soils, one on the left is a very well-drained brown earth soil, the other on the right is a very poorly drained clay soil, and that means that water in these soils flows very differently. So on the right, in the poorly drained soil, water will tend much more to flow over the surface of the soil, whereas on the left, in the well-drained soil, it will tend much more to percolate down through the soil, and that has implications then for nutrients and whether they might be lost or not. So in general, a poorly drained soil like that will be considered more risky in terms of phosphorus loss, because overland flow will tend to pick up the phosphorus from the surface, including on the particles that might be washed off in the runoff. And the well-drained soil in general will be regarded as more nitrogen risky, as water will tend to move down through the soil and potentially leaching out nitrate from the soil. And so this means that we, in addition to soil testing and managing according to the soil tests, we should be taking into consideration what the soil type is itself. And of course, farmers will know on their farm what their soils are like and how they behave differently in this way. What I saw there in the video is, has some information in reference to the PIPs, which are these maps produced, which indicate exactly this kind of thing, where soils might be more risky in terms of phosphorus loss by a runoff or by a nitrate leaching. So those are useful things to have as a tool. Just to give this, and that leads into the concept of a critical source area. So in fact, many studies have shown that a very small areas within a catchment or within farms actually can contribute the lion's share of the nutrient loss, particularly with phosphorus. So as a general sort of rule of thumb, 90% of the phosphorus could come from just 10% of the land in just a few events, often, especially in Ireland during the winter with big rainfall and runoff events. And so that's the idea of critical source areas. And the idea is that you could focus management on those in order to prevent that loss from happening. So we would have looked in some of our research at different factors that would be contribute to creating these critical source areas. So for example, and this is again from the agricultural catchments program, the soil type. So coming back to that, whether it's well drained or poorly drained type soil, the soil phosphorus status, so whether it's high in phosphorus or low, the topography, so how the landscape is, how water flows in the landscape, and that's related to things like slope, as you can see there, or connectivity, how connected something is to a receiving stream, and from that you can build an idea of where these critical source areas are, and that's something very similar to what is behind the PIP maps. From some of the studies we did there, just to show you what this looks like when we were modeling these critical source areas and pathways by which nutrients leave the fields and the farm. So this is what was modeled, and then this is what actually happens during a big rain event, and you can see how those areas, which during dry conditions might not seem very obvious, but during big rain events, this is how a lot of nutrient and also sediments can leave the farm. So the implication is that if you see those green and blue points there on the map, there are places where you might be able to put something in place to intercept and prevent those nutrients and that sediment from leaving the farm, such as maybe a small buffer area, as was mentioned in that video, with some vegetation left that can help to slow down that water flow and capture that sediment. Okay, and measures like that, so a setback distance or a buffer up to a stream edge, for example. Okay, how am I doing there on time, Adele?
You're going good. You can keep going if you like, Paul. I don't think there's any time pressure. If you want to finish up, that's fine.
Absolutely fine. Absolutely fine, Paul. Keep going. You did plenty of good information.
Yeah.
Okay. Great. I actually forgot to mark the time when I started, so I don't know. So just the third thing I wanted to talk about, and I know there's a lot on this. So this is from the published paper that this work was in. It's around grass clover and multi-species, which again I was happy to see was highlighted in the videos. So we've been doing some work at UCD now at Lyons' farm, looking at grass clovers and multi-species. Helen Sheridan in particular has been leading all of that up, and there was a research project called Smart Grass a few years ago, which looked at these. There's a lot on this graph, so I only just want to highlight a couple of things as take-home messages from it. What this is showing is grass growth or yield in kilograms dry matter per hectare. So, what I've highlighted there as red is from the yield over 2 years from a perennial ryegrass sward at 250 kilograms of nitrogen fertilizer. And then for comparison, grass clover and multi-species swards at different fertilizer nitrogen rates, and those fertilizer nitrogen rates are along the bottom in kilograms nitrogen per hectare per year. So our benchmark, or what we're comparing against, is that red line. That's the perennial ryegrass with high nitrogen, 250 kilograms fertilizer nitrogen per year. The two I've highlighted here are two grass clover mixes. So 40% grass, 60% clover, and a 70-30, 70% grass, 30% clover mix. You can see that the high clover one actually outyielded the ryegrass, even at zero fertilizer nitrogen input, which shows you how much dry matter can be got from clover. And the lower clover content, 70-30 one there, the green dashed line, catches up with the high nitrogen perennial ryegrass as somewhere between 45 and 90, maybe about 60 kilograms of fertilizer nitrogen per hectare per year. And then two of the multi-species, which is bringing grass, legume, and herb in. And you can see how they're at or about, one of them is lower than the perennial ryegrass initially, and then they, similar to that grass clover there, at around 60 to 90 kilograms per hectare per year of fertilizer nitrogen, they are able to match the ryegrass yield. So that's the important thing about this, is that that's showing that you can match the yield with much reduced fertilizer nitrogen input, and that's the important thing for water quality. That means much less risk of excess nitrogen and losses of nitrogen to water, and also the other emissions that are associated with fertilizer nitrogen, which would be nitrous oxide, which is the greenhouse gas, and potentially ammonia emissions. So anything we can do, and this is, anything we can do really to optimize fertilizer nitrogen use, reduce excess fertilizer nitrogen use, is has multiple benefits actually. I'm just going to go through that and just finish up with this, which brings us on to an experiment that some of you may be aware of, but that we started a couple of years ago at UCD Lyons' research farm, where we've gone from the plot scale sort of experiment, which is what the results I just showed you there, up to a farmlet scale. So we now have 3 farmlets there, one based on the perennial ryegrass system, one on a grass clover, and one on a multi-species sward, which you can see in that picture there. And they are on a dairy calf to beef system. So each one of those is managed as its own little farm, if you like, with its own herd of 20 animals grazing only that sward. So the idea is to see how that system performs. And one of the things, of course, we're interested in is how that might affect water quality. So one of the things we did, and just finish up on this, when we were putting those swards in, we did quite a bit of work around the paddocks that we were putting in to what we call hydrologically isolate them. So we put French drains like this. So we dug a trench, put perforated pipe in at the bottom, and a stone backfill to the surface. And that's around the downflow end of each of the paddocks of these different sward types, so that we could collect the water that would run off them and monitor the effect potentially of these different swards on nutrient losses, for example. So this is work that we're now starting to do. So what you see there on the bottom right is flumes. So the water that's draining off of these areas of grass and grass clover and multi-species, they come to points here where we can monitor the water that's coming off them and monitor the impact on nutrient losses. Okay, I think I'll leave it with those nice pictures. That was a lot of work doing all of that, and hopefully now in the time to come, that's going to bear fruit. Hopefully, in terms of what we'll find, it's important to actually be able to measure the impact of these things and show the effects that they are having.
Okay, well, many thanks, Paul. There's a lot of very interesting, I suppose, very up to date and but very relevant pieces of information going on. And the president referred to obviously the climate targets that will be attributed to us in agriculture. And if there was ever a time that we need good research, it's now and for the next 10 years. So, best of endeavours in your going forward.